In this video, we will continue to look at electrical quantities. In previous videos, we would have looked at electrical charge and current. We would have actually defined electric current in terms of the flow of charge. We would have also looked at briefly at resistance. We also looked at the comparison between EMF and PD, and we spoke about both quantities being defined in terms of the energy changes that were taking place. In the case, of course, of EMF, we spoke about battery or source converting other forms of energy into electrical energy. And in the case of passive devices like resistors, conductors, and so on, we spoke about them converting electrical energy into other forms like light, sound, and heat. So in this video, we started by looking at electrical power. Now, from previous parts of physics, we would have met power before. And what exactly is power? How is power defined? Power is defined as the rate at which work is done or the rate at which energy is converted, right? So power is the rate at which work is done or the rate at which energy is converted. So whenever a body does work or convert energy from one form into another, the rate at which it does so is its power. Now, as we mentioned earlier, electrical power, or, well, not electrical power, but there are certain devices which convert energy. When you speak about a battery or source, they convert other forms of energy, for instance, chemical energy into electrical energy, right? And the rate at which they do so is the power of that battery or source. Also, when you speak about passive devices like resistors or conductors or even a lamp, basically, they do the reverse. They convert electrical energy into other forms of energy, particularly light and heat and so on, sometimes sound. And the power of those devices refers to that energy conversion, right? So we could basically say that the electrical power or the electric power or just the power of a battery or source is the rate at which it converts other forms of energy and, for instance, it could be chemical, it could be mechanical, etc., into electrical energy. Right? So the power of a battery or source is the rate at which it converts other forms of energy, chemical, mechanical, etc., into electrical energy. Now, in a previous lesson, we would have actually met the equation which relates energy, charge, and voltage. And this equation, of course, was W equals QV. So basically, or in the case of, in the case of a source, we normally use, E for EMF. But of course, if you're simply calculating power, you can actually just use the symbols interchangeably, right? But just to be correct, we'll put E for, no, we'll just put V. Let's just work with V. So W is equal to QV. All right, so W is equal to QV. Power. So we say power is equal to work done or energy converted divided by time taken. So using this formula, we can then now say that P is equal to W over T. But of course, W is equal to QV. So this gives us QV over T. But of course, if we recall, we can recall that electric current is defined as the rate of flow of charge. So therefore, we can say, but I equals Q over T. So from this equation, we see that the Q over T will be equivalent to the current I, and therefore this means that power is equal to IV. So what that formula shows is that if we know the current flowing and the PD across the device, we can actually calculate the power, right? If it's a battery, we can basically calculate the power being delivered to the circuit for a battery or source. If it's some other device which is actually using up electrical power, we say that we can calculate the power being dissipated in that device. So these formula will apply to the power delivered by a battery to a circuit, or battery or source to a circuit, and they can also use to calculate the power being dissipated in some passive component like a resistor or a conductor. Now, there are other versions or other versions of this formula which can be used to calculate power. So let's derive those other equations as well. Now, if you recall from Ohm's law, V is equal to IR. So if we substitute for V into this equation, we therefore get P is equal to I times IR, and therefore this means that P is equal to I squared R. So this formula is one of those which is generally used to calculate the power dissipated in a device like a resistor. P is equal to I squared R. So it's the square of the current times the resistance. We can also use or derive another version of the same equation, this time in terms of V. So from this equation, V equals IR, it would mean that I equals V over R. And so if we were to substitute for I in this equation, we'll get the equation for power in terms of the voltage and the resistance. So substituting, so we get P is equal to V over R times R, and so we get P equals V squared over R. And these are the equations that we'll generally use to calculate power. If we're talking about power being delivered by a battery or source, we typically use P equals IV, right? That is, of course, provided we didn't already have how much energy was being delivered or converted. We could also divide the energy by the time taken. But if we have the current being delivered by the battery and we have the EMF, then we can calculate the power delivered by the battery using the formula P is equal to IV. Now, these two other versions generally are not used for batteries or sources, but they're actually used to calculate the energy being dissipated by or within a particular component, and in most cases, this energy is in the form of heat.